Hi class, this is Blair. In this video we are going to be going over 8.1 examples. Okay, so that's converting from Cartesian to polar and polar to Cartesian, and hence the double-headed arrow. Okay, so the first example, we are going to start with a polar point. Okay. First, we are going to go over how we plot this polar point, and then as well as listing other representations, so other ways that we can express this exact same polar point, as well as converting to Cartesian coordinates. So let's first plot this polar point. So we have some radius of 1, say, right there. Another radius of 2 circle. Sorry, bear with my pickiness to make it look good. Some radius of 2 circle. Okay. And what we do is we extend out by 2 and we rotate up by pi thirds. So that is that point right there. Okay, actually, yeah, we can draw that line. Doesn't really matter. But either way, that is how we plot the point 2 comma pi thirds. Okay. And I just realized that I had that copied down wrong. This should be r and theta. Okay. So 2 being your radius, theta being pi thirds. Okay. Now other representations. We could take 2. So we could take a radius of 2, which would be right there. And we could rotate around and around again. Okay, so we're basically just taking that pi thirds angle and we're adding 2 pi to it. So pi thirds plus 2 pi is going to be 7 pi thirds. Okay, let's do another one with a positive radius. We could take 2 and we could subtract 2 pi. So let's erase this. And we could take this and rotate around this way. Okay, so that ends up being negative, let's see, negative 5 pi thirds. Okay, let's also list 2 representations of a negative radius. Let's change colors for that. Let's do blue. Blue might be fun. So we could have negative 2, comma. Now let's kind of sketch this out a little bit. What we really want to rotate to is this line down here. Okay, so we could rotate down this way, because when we rotate down this way and then we extend out that opposite direction, we end up getting this point again, okay, which is the ultimate goal. Okay, so now we just need to figure out, well, what is this angle right here? Well, this angle right here just ends up being pi thirds minus pi, right? Because we just take that piece right there. Let's actually maybe dash line that piece and subtract pi from it, and then we end up getting there. Okay, and pi thirds minus pi ends up being negative 2 pi thirds. Now that we have this base angle for our negative radii, we can just add and subtract some multiple of 2 pi from this guy right here. So we could take negative 2 and add 2 pi to negative 2 pi thirds. Okay, so So negative 2 pi thirds plus 2 pi ends up being 4 pi thirds. Okay, and that ends up being this rotation in order to get to this exact same point, but then we end up moving inward rather than outward on a radius. Okay, and these are 4 different representations to express this exact same point. Okay, now let's convert to Cartesian. So when we're converting to Cartesian, this is the one that we didn't really talk much about in the lecture notes, but it's because it's so simple. We know x is equal to r cosine of theta. We know y is equal to, missing a piece, r sine of theta. And we really don't need to memorize that because we just have this triangle right here. Let's erase this 2. It's this right triangle. We have this theta right here. We have 2 being this hypotenuse. And if we were looking for this x and this y. If we were looking for x, we can use cosine of theta. So we can say cosine of theta is equal to x over 2. And we can say that sine of theta is equal to y over 2. Okay. Well, that 2 is just that radius. When we multiply it over, that's where we get this component right there. Okay. So now x is equal to 2 cosine of pi thirds. Y is equal to 2 sine of pi thirds. So cosine of pi thirds from your unit circle, make sure you're not really trying to fight the urge to use your unit circle, because remember, that's just this small increment going to the right, so that ends up being 1/2. So cosine of pi thirds is equal to 1/2, and 1/2 times 2 is equal to 1. And sine of pi thirds is equal to square root of 3 over 2. And so square root of 3 over 2 times 2 just ends up being equal to square root of 3. So ultimately, our Cartesian equivalent representation ends up being x comma y, which is 1 comma square root of 3. So if we were to erase all of this stuff that I had just drawn up here, and I don't want to erase everything, we'll leave it at that. We can say that we have to go to the right by 1 and up by square root of 3. And we end up getting this exact same point. Okay, and that is all you have to do for converting to Cartesian for a point. Okay, it's a little bit more complicated when we get into equations in the next lecture video, but you will see that soon. So let's now talk about converting from Cartesian to polar coordinates. First example is a very simple one. Second example is a little bit more complicated. So let's do the first one. So when we're converting from Cartesian to polar coordinates, the components that we need to know is our Pythagorean theorem. And we also need to know tangent of theta is equal to y over x if given that x is not 0. Okay. So we can solve for r squared. R squared is equal to square root of 2 squared plus negative square root of 2 squared. Square root of 2 squared ends up being 2. Negative square root of 2 squared ends up being 2. So we get 4. When we take the square root of both sides, r is equal to plus or minus 2. Okay, so that means that we can extend inward or outward, right, which is what we already know. Then tangent of theta is equal to square root of 2, our y component, over negative square root of 2. That negative can be pulled out front, and we can manipulate this by dividing the top and the bottom by 2. So we have square root of 2 over 2 over square root of 2 over 2. Now we can relate this to our unit circle, and we just need to consider this negative being in the numerator or in the denominator. Okay, so if we were to analyze this a little bit, we'd have x and y, and if our negative is in the denominator, it means it would be going up by square root of 2 over 2, and to the left by square root of 2 over 2 till we get here. So that is going to be a rotation of 3 pi fourths, or we could go down square root of 2 over 2, and to the right square root of 2 over 2, so that we can rotate by negative pi fourths to get to this point down there. So we can say that theta is equal to 3 pi fourths plus 2k pi, or negative pi fourths plus 2k pi. Okay, so when we're converting to polar, we can choose one of these pairings. We can always check our work too and our understanding and make sure that we picked a correct one. So if we chose a positive 2, and we know that we wanted to be up here, that means that we'd want to rotate positively in order to get there. So we'd take 3 pi fourths. And you can always add some 2k pi to this. Doesn't really matter. We also have equivalent representations that correspond to this negative as well as this bottom component for theta. So we'd have negative 2 and negative pi fourths. And we can also add some 2k pi to that negative pi fourths. Okay. And either answer is fine. Doesn't really matter which one you choose, unless if it specifies that it wants, say if it specified in a question that it wanted it to be a positive radius and a positive rotation in between 0 and 2 pi, then you would be basically pegged to using this answer. Okay. Otherwise, you're more than welcome to use whichever one you feel most comfortable with. Okay, part B, we have 6, 8. So we can use Pythagorean theorem. R squared is equal to 6 squared plus 8 squared, which is equal to 36 plus 64, which is equal to 100. So that R is equal to plus or minus 10. Now this is when this problem gets a little bit more complicated than part A. Its tangent of theta is equal to 8 over 6, if we simplify this down, so it'd be 4 over 3. There's no way that we can manipulate this, that's why it gets a little bit more complicated. So we actually need to say that theta is equal to tangent inverse of 4 over 3. See, inverse tangent popping up again to haunt us in our nightmares. So let's continue on with this one and how we can actually perceive this. So we know that theta is equal to this tangent inverse plus 2k pi, but now we need to be able to know, like, what is this or, right? And so we need to actually know, where is this lying? Well, we know tangent inverse is lying in between negative pi halves to pi halves, and since we have a positive input, that means it's going to be rotating positively upward. So we have x and y, means that theta is going to be somewhere over here. Okay. But note we could always have, say, a negative over a negative, right? Which will end up giving us a positive in the long run. So we'd have a negative 4 right here and a negative 3 right here in order to get right here. Keep in mind that this is still theta right there. And so we're going to call this entire rotation, we can say that we have pi plus some theta, right? So we could say or pi plus tangent inverse of 4 over 3 plus 2k pi. Okay, so we're basically just offsetting it by this pi. Okay. Now, ultimately, we can pick our representation. We can say r comma theta is equal to 10, positive 10, and then say we rotate it out there so that we got to this point, so that we would take tangent inverse of 4 over 3, and remember, we can add some 2k pi to this. Doesn't really matter if we subtract 2 pi or 4 pi or add 6 pi, 8 pi, 10 pi. It's always going to give you and end up at this exact same point, which is our desired point. And we can also have a representation for negative radii. So negative 10, and we could take pi plus tangent inverse of 4/3. And this also applies for down here. Okay, so we could add 2 pi to that. And so we could say that another representation for this angle, if we were to add 2 pi to it, we could say that 3 pi plus tangent inverse of 4 over 3 gets us to this point if we have a negative radius in order to rotate inwards. But either way, both of these answers are completely okay. And that is it. So that is it for this lecture video for examples for 8.1, and I will see you in the next lecture video for 8.2 examples.